Welcome to Winning Edge. Today we will discuss electrochemistry. Electrochemistry have a huge applications in our chemical energy storage, and that subsequently used as electrical energy in plating metals or plastics or other metals, like whatever our bathrooms, faucets and fittings we use. They are mostly polypropylene based and having metallic finish, which is electroplated, of important metals which are purified using electrochemistry, or small batteries that we'll use in our portable devices, or any other purification like aluminium purification. They all having use of electrochemistry. Let's try to see the basics aspects in electrochemistry. The very first thing we want to see is electrochemical series. What is electrochemical series? In the electrochemical series, elements are placed in decreasing order of their standard electrode potentials. In other words, standard electrode potentials can also be called standard reduction potentials, as we see here in table. The topmost reduction is of fluorine, 2.87, because of its high electronegatividity. Standard reduction potential is very high. Similarly, going from fluorine to hydrogen, whose standard electrode potential is fixed at 0. All other elements in this electrochemical series are placed with respect to hydrogen, having a standard electrode potential higher than hydrogen. They are placed like that, and relatively having a standard electrode potential lower than hydrogen, then they will be placed at the bottom of the table. Next is your cobalt 3 positive. It is reduced to cobalt 2 positive, 1.81, and all the topmost elements in the electrochemical series are strong oxidizing agent. The reason is because they can oxidize other species by taking electron. Or the next species formed is the weakest reducing agent, because the reverse of this reaction is conversion of fluoride into fluorine, which is a losing electron or providing electron. So it is acting as a reducing agent, and it will be minus 2.87 here, fluoride, which is weakest reducing agent we have. Now going to the bottom of the series, as we discussed, hydrogen is referenced to 0, and lithium, which is the bottommost element of the table, having a standard electrode potential minus 3.05. It means lithium reduction will be to lithium atom having a reduction potential of minus 3.05. It's a strongest reducing agent. Why? Reducing agent means that provides electron for reduction of other species. This is the reduction potential. For lithium to act as a reducing agent, it has to provide electrons, or it will provide, we have to look for the oxidation of lithium here. As we just know, that can be done by reversing the sign. Minus 3.05 will be plus 3.05 volt. Lithium to lithium ion and electron. So lithium is providing an electron, with standard electrode potential 3.05. Now we know for a reaction to be feasible, delta G should be negative, and delta G is equal to delta G minus NFE, mean negative sign and electrode potential. N electron is 1, F is fixed, and electrode is 3.05 for lithium to lithium ion, because here, as we told, sign is reversed. That's why it is acting as a strongest reducing agent. Electrochemical cells. Here we are talking about oxidation of zinc, reduction of copper ion, and it together makes a electrochemical cell. Elements with higher standard electrochemical series potential can accept electrons easily, so they can act as a stronger oxidizing agents. We are talking about in the same series. So element lying above the hydrogen can accept electrons because of their positive standard electrode potential. Like copper, we know is having a standard electrode potential 0.34 volt. Elements lower in the standard electrochemical series, that is like zinc, which lies below the hydrogen, having a electrode potential minus 0.76. So it acting as a stronger reducing agent for a species that can provide electron to other species. That's what exactly happens. This is electrochemical cell. Positive side called cathode, negative side called anode. Or anode is the electrode on which our oxidation happens. Because zinc oxidizes, leaving electron here. That's why this electrode is negatively charged. And cathode is an electrode on which reduction happens. Because copper ions get here deposited, so copper get reduced to copper 2 positive to copper. This is an example of Daniel's cell, and this electron supply is used. The potential difference develops between the two electrodes is depending upon the propensity or the standard electrode potential differences between the two electrodes. So it is a potential difference that develops between the electrode and its electrolyte. The electromotive force is the maximum potential difference between the two electrodes of a galvanic or voltaic cell. So this potential difference between the two electrodes is known as EMF. Cell potential will be electrode potential of cathode minus electrode potential of anode, which is 0.34 minus 0.76. Total potential will be 1.1 volt. We know as zinc started to oxidize, zinc ion concentration in solution will increase, and sulfate concentration will increase here because of the enhanced deposition of copper on the copper electrode with time. That causes a voltage to drop because excessive positive charge and excessive negative charges will start polarizing the solutions close to the electrode. The answer to this was how to neutralize these excessive charges. The concept of salt bridge was introduced. This is a salt bridge. To maintain the electrical neutrality in the individual half cells, excessive charge has to be removed. That is done by salt bridge. What salt bridge do? Salt bridge provides a medium for these both charges to be exchanged. zinc moves, positive charge move from here, negative charge will go from the cathodic side and get neutralized through the salt bridge. So the excessive potential developed in the solution will be neutralized. These excessive positive or negative charges are neutralized through salt bridge. That is the reason we get it. We just got rid of it. Next is measurement of electrode potential. Standard hydrogen electrode consists of a platinum electrode coated with platinum black. The electrode is dipped in an acidic solution and pure hydrogen is bubbled through it at 1 atmosphere pressure. Fugacity 1 means it's for a gaseous gas bubbled through at 1 atmosphere pressure. It is a partial pressure of the gas, which is hydrogen here. Here it is connected to a salt bridge and we bubble hydrogen here so that hydrogen ions concentration is maintained. This is known as the half cell reaction or standard hydrogen electrode, with respect to which all standard electrode potentials are measures for different elements. We know copper dissolves in nitric acid but not in HCl. The standard electrode potential for copper we know is 0.34 volt. That is the reason it can't be oxidized for the reduction of protons in HCl. And chloride, we know it is a very weak reducing agent. That is the reason. And chlorine is a very strong oxidizing agent, but chloride is a very weak reducing agent. So even chloride nowhere involved in the reaction with copper. That's why copper cannot react with HCl. But in nitric acid, copper is oxidized by the nitrate ion. So we have to think like that. Copper is not reducing hydrogen, but copper is getting oxidized by the nitrate ions. Let's see an example. Copper in nitric acid. It forms copper nitrate, and nitrate of the nitric acids, they got reduced to nitrogen dioxide, and water, this hydrogen or nitric acid remains same here in a positive oxidation state. So this is one of the example. We can try to understand how the electrochemical series helps to understand the chemistry of reactions of different elements with respect to different acids or alkalis. Now, how we represent an electrochemical cell, let's try to understand. The cell anode and cathode, which are half cells, are separated by the two bars. So two half cells are separated by these two bars, which is called a salt bridge, with anode on the left side. Anode we know in our electrochemical cell on the left side, and cathode on the right side. So here on left side on anode, oxidation do occur. On cathode, reduction do occur. So here we have a standard hydrogen electrode. That's why we are representing electrode like platinum solid, single bar, which separates from electrolyte. Here it's a hydrogen. In gaseous form, condition is 1 bar. Again, it gets oxidized to proton Aqueous again, 1 molar concentration of acid that is maintained by bubbling of hydrogen at constant 1 bar pressure. And on our cathodic side, we have a copper aqueous solution, 1 molar concentration. It got reduced to copper. Similarly, our Daniell cell we can represent, we know our anode is zinc that got oxidized to zinc plus ions, and our cathode will be copper, in which copper ions are reduced to copper. So that's why our leftmost is zinc solid electrode. It get oxidized to zinc ion, which goes to aqueous solution. Whatever the molarity maintained, we can write there. Salt bridge. Copper, 2 positive ions, which are aqueous, 2 positive. It got reduced to copper solid. So this is a simple representation of Daniell cell.